All right, gentlemen. Today is Tuesday, April the 7th, and today we are going to talk about simple harmonic motion and how it can be described. Now, this video has a lot of slides in it, and therefore I'm going to have to go very quickly through most of them. So feel free to pause the video and examine the slides or do whatever you have to do in order to keep up. So, we're going to start by describing simple harmonic motion of a mass attached to a vertically hung spring. Now, the mass will start at its maximum positive displacement, which is at this level, all right? And this is step one that we're talking about. The mass starts at its maximum positive displacement, y equals a. The velocity is 0, all right? You can see that here. And the acceleration is negative because there's a net downward force, right, bringing it down. Now, at step 2, the mass is now moving downward. So the position is decreasing, and the velocity is still negative at this point. All right, you can see that right here. As the mass nears the equilibrium point, the restoring force and therefore the magnitude of the acceleration decreases to, it's getting smaller. And at step 3, where we've reached the equilibrium point, now the mass is still moving downward, so the position is 0, but the velocity is at its maximum, all right, negative maximum, but still maximum. And so the net force at this point is 0, and therefore the acceleration is 0. At step 4, the velocity is still negative. All right, you can see that here. But the magnitude of the velocity is decreasing because we're going back toward the equilibrium point. And now the acceleration is positive. At step 5, the mass has reached its lowest point of motion. All right, and so we're now at negative a in terms of amplitude, which is its turning point. And so here's the negative amplitude. At this point, the velocity is 0, okay, because it's stopped again, and its acceleration is maximum in the positive direction, right? Because now it's going to start accelerating upward. The mass is at step 7. The mass is passing through the equilibrium position again, but in the opposite direction. So it has a positive velocity. You can see that right here. But it's got the acceleration is flipping from positive to negative at step, and so therefore it's 0. At step 8, the mass continues moving upward. The velocity is positive, but its magnitude is decreasing, and therefore the acceleration is negative. And finally, at step 9, the mass is now starting back to its starting position, and we're right back to where we started at step 1. Okay, so the position versus time graph represents a cosine curve. Let's go back, all right? Position versus time is shown here. All right, so the position at time t is given as the amplitude times the cosine of 2 pi t over the period. All right, so position is a function of time. I know all of you guys who are in calculus are loving functions and all of that kind of stuff. And so therefore, the cosine function can be written in terms of the frequency rather than time over the period. And so the position is a times the cosine of 2 pi f times time. The velocity time graph is an upside down sine function. Okay, and you can see that here. And so v of t is equal to the opposite of v max times the sine of 2 pi t over a period, or, darn it, negative v max times the sine of 2 pi times the frequency times the time. We can then use that to calculate the acceleration because we know that F net over m is equal to a, or in the case of a spring, the spring constant over the mass times the displacement gives me the acceleration. acceleration. And so therefore the acceleration is equal to a times the cosine of 2 pi f times t. All right. This is a great little slide because it does illustrate the positions here and here at given times that you can see here, depending upon where you are in the period. All right. I suggest you pause the video and look at these two graphs as well as the mathematical relationships in the table at the bottom. So let's look at an example problem here. In example 14.2, we have the motion of a glider on a spring. So an air track glider oscillates horizontally, so back and forth, on a spring at a frequency of 0.50 hertz. Suppose the glider is pulled to the right of its equilibrium position by 12 centimeters and released. Where will the glider be 1 second after its release, and what is its velocity at this point? Okay, well, if we pull this thing, this is the position time graph. And so here we are at 12 centimeters here. And we want to know, because the frequency is half of a hertz, that means that the period is 2 seconds. And so therefore, at 1 second, we will have completed half of the cycle here. And so we'll be located at this position here. All right. So negative 12 centimeters. We want to know what the velocity at that point will be. Well, the glider undergoes simple harmonic motion with an amplitude of 12 centimeters. Because the frequency is 0.50 hertz, the period is 2 seconds, right? 1 over 0.5 is 2. The glider is released at maximum extension from the equilibrium position, so we can take that point to be time equals 0. 1.0 seconds is exactly half of the period. And so as the graph of the motion in the figure shows, half a cycle brings the glider to its left turning point, 12 centimeters to the left of the equilibrium position. And we know, of course, that the velocity at this point is 0. Okay, so let's move on to something a little bit different. This is kind of a neat little thing that we never really talked about when we did circular motion. But let's say you've got a wheel, the tire on a car, and you paint, a point on one point on the tire, like is shown here. Now, this is a tennis ball or something glued to a circular turntable, and there's light being shown from the top. Well, this shows the shadow of the ball, and the shadow is going to move back and forth and back and forth and back and forth. And this is going to be simple harmonic motion. It's exactly the same motion that we would witness. The motion of the shadow is exactly the same as we would see with the block attached to a spring moving horizontally. Now, the x component of that circular motion, when the particle is at angle theta, is going to be equal to a times the cosine of theta. All right, so here's the length of the rod, the amplitude. Here's the angle theta in here, and so the distance that we see here is going to equal a times the cosine of theta. It's the same as this distance here. Now, the velocity, because we're moving tangentially at a velocity of 2 pi times the frequency times the amplitude, and the acceleration is going to be 2 pi f squared times the amplitude, okay, based on the equations that we saw earlier, and the knowledge that theta is going to equal the omega times t, the angular velocity times t, and the angular velocity, of course, is 2 pi times the frequency. Now, so the particle's x component can be expressed as the amplitude times the cosine of 2 pi times the frequency times the time. And this is the same as the equation for the position of a mass on a spring. The x component of a particle, therefore, in uniform circular motion is simple harmonic motion. So here, this is essentially the proof. All right, the velocity is also corresponds to simple harmonic motion. You can use the same equations to get our maximum velocity equivalent to 2 pi times the frequency times the amplitude. The acceleration, again, can be calculated this way. And the maximum acceleration is going to equal 2 pi times f quantity squared times the amplitude. And so therefore, the moral of the story is if I know the amplitude and the frequency of an object in simple harmonic motion, we can calculate the displacement, the velocity, and the acceleration using the three formulas that you saw. Now, I love this graph or this chart because it shows the position graph, the velocity graph, and the acceleration graph, along with the formulas that I didn't even touch the mouse that time. The formulas that we can use to calculate these things. Okay, so here they are. Now, question 14.3, measuring the sway of a tall building. All right, tall buildings move. If you've ever stood on the observation deck of the Empire State Building, you know that it moves. The John Hancock Center in Chicago is 100 stories high. Strong winds can cause the building to sway, as is the case with all tall buildings. On particularly windy days, the top of the building oscillates with an amplitude of 40 centimeters, 16 inches, and a period of 7.7 seconds. What are the maximum speed and acceleration at the top of the building? So the building is literally swaying back and forth with simple harmonic motion every 7.7 seconds. So I've got an amplitude of 40 centimeters that I'm going to have to calculate to meters or convert to meters, and I've got a period of 7.7 seconds, from which I can calculate the frequency. So we're going to have to assume that the oscillation of the building is simple harmonic motion with an amplitude of 0.40 meters. The frequency can be computed as 1 over t, and 1 over 7.7 is going to give us 0.13 hertz. So therefore, we can then use the equations for maximum velocity and maximum acceleration to calculate. The maximum velocity is 2 pi times the frequency times the amplitude, which gives us 0.33 meters per second. And the maximum acceleration is 2 pi times f squared times the amplitude, which gives us 0.27 meters per second squared. And so that's a fairly small acceleration in terms of free fall or the acceleration of gravity. The acceleration is only 0.027 times the acceleration of gravity. So you don't really feel yourself accelerating all that much. So if the acceleration is quite small, as you would expect, because if it was large, the building acceleration occupants would be complaining about the acceleration. So even if they don't notice the motion directly, office workers on high floors of tall buildings may experience a bit of nausea when the oscillations are large because the acceleration affects the equilibrium organ of the inner ear. All right, fellas, that brings us to the end of section 14.3. I know that I went through that really, really fast. However, read the textbook and have a look at homework questions 6 through 16. These we do at the end of business today, but I will accept them right up until Friday of this week. Okay? Follow the instructions and send me a photograph.